Stanford University.
This talk is about research that we're doing for GCEP, and it's being done by 4 universities. University of Illinois is one of the participants, and that's where I'm at. Northeastern, University of Tennessee, and Rensselaer are my other universities involved in this, so we're all working together on this. In this talk, given the audience is kind of diverse, I decided I'd give more of a general talk about the reason why we're doing this research, show a little bit of interesting aspects of it, then the posters cover more details on the specifics. So it's going to be a little general. Secretary Schultz did a really nice job in the interview, and it provides a nice tie-in with this talk because we're talking about energy and the importance of energy, and the electric grid plays a large part in that. This slide here shows our energy source pie, and right now we're about 80% fossil fuel, and if we want to decrease that, we're going to have to transition to more renewable forms. Of those renewable forms, most of them come to us in the form of electricity. Right now, about 40% of our energy is consumed in the form of electricity, and we're working to increase that, particularly in the area of transportation. In 2009, though, very little of that came from wind and solar. About 0.75% came from wind, and less than 0.1% came from solar. Certainly areas that are growing, and that's the focus of our work, is to see how we can get more in that area. We heard a wonderful presentation this morning about natural gas. I really want to highlight the importance natural gas plays in integrating renewable energy into the electric grid. This graph here shows the ups and downs, the roller coaster, I guess, that Secretary Schultz was talking about in the price of natural gas. And if you look towards the end there, just in the end of 2008, natural gas prices were very high, and some of us, myself included, thought they weren't coming back down. And then suddenly natural gas prices came down quite a bit. And the reason why this has a big impact on the electric grid is, as was mentioned this morning, natural gas is becoming a larger and larger source of electric generation. GE and other companies are very efficient in building turbines that can take natural gas and convert it into electricity. So when when natural gas prices are low, that means electric prices are low as well. I did want to mention, as we talk about generation sources, there's a difference between capacity, that's how many megawatts you have, and energy. Energy is how often you use those megawatts. Some sources, like nuclear, are used quite a bit, and they have very high capacity factors, whereas others, like oil, aren't used as much, and they have very low capacity factors. So just because you have a lot of capacity in one area doesn't mean that you're going to get a lot of energy from that source. Well, where do we get our electricity currently? Here's a bunch of figures that show where we get our data in the upper left, or where we get our energy in the upper left. Coal is the largest source, but it is decreasing, as we saw earlier. Natural gas is second, and it's growing. Nuclear is at about a third source. About a fifth of our electric energy comes from nuclear. Hydro's fourth, and then other renewables come into play there. But the graph on the right shows that where we get our energy varies quite a bit by state. Out in California, you use natural gas, hydro, and nuclear. That's the brown, the red, and the blue dots there. Hydro is very big in the Northwest. If you look in the Midwest, where I come from, those black dots predominate. We've got a lot of coal generation in Illinois, Indiana, Ohio, down in the South. Coal is really big in some areas. So just because we get 40, 50% from coal doesn't mean every state does that. So this has an implication if we try to transition from one energy source to another. So you have to look at what sources are available in particular states. The graph on the bottom left there shows where we have added generation capacity over the last 80 years. If you look at 2000 and you see that big yellow spike, that's all natural gas generation that was built very quickly over the last decade, and there's a lot of natural gas generation around. So now that we have very low natural gas prices, there's a lot of generation, it's driving down electricity prices, and if you're trying to compete with that with wind, it's very difficult. Okay, wind does much better when the electric prices are high. The green that's showing up on that graph towards the far right is the growth in wind power. So if you look at the paragraph there on the right-hand side, wind provided 2.3% of our electricity in 2010, but just this year in the first half, it's gone up to 3.2%. So it's certainly a rapidly growing area, as is solar, although solar is starting at a smaller amount. This is a graph of our transmission grid in the US. If all you take away from this is it looks like a mess, that's fine. It's a big mess. But as power engineers, we know this mess quite well, and how that mess operates, all the intricacies have a big impact on how much renewable generation we can integrate into the system. So what we're doing on this project is we're looking at transmission models and playing around with various techniques to try to integrate in more and more renewable generation. But on the bottom right there, I show the different interconnects. There's 4 major interconnects in North America. The east is shown in blue, the west is shown in green. Texas, being Texas, is its own interconnect, and then Quebec makes up the last part of it. Before going forward, I did want to make a comment on the idea of a smart grid. We engineers like the fact that there's been a lot of research and push in the smart grid area right now, but you don't have to scratch too far in the power engineering community to realize that a lot of us don't like the term smart grid in so much that it implies that the existing grid is dumb. My favorite ad from the 2009 Super Bowl was GE's ad where it's called If I Only Had a Brain, where they got a scarecrow dancing in a substation singing If I Only Had a Brain. And it was a cute ad, and but GE and power engineers know GE's been building equipment for a long time, and I can tell you it's got brains. And there's a lot of brains in the power grid. We aren't quite as dumb as people think, but of course we can all get smarter, and that's what we're working on in the smart grid. But an important point as we move forward is from the customer point of view, we've really in the power industry designed a very simple user interface. We did plug and play long before the computer industry. Plug it in, play it, and it works. As we move forward with the smart grid, we want to make sure we don't, by getting smarter, lose this simplicity so that suddenly people have to make a reservation to plug in their toaster. Well, what makes the grid unique? There's a couple of aspects that, when taken together, really present some unique problems for the power grid. First, in contrast to some other infrastructures, stuff moves fast through the power grid. Electric disturbances propagate at almost the speed of light. So very quickly you can have electrical disturbances propagate through the system. Even mechanical disturbances propagate at maybe 500, 600, 700 miles a second. So things move very quickly. But we also have an issue where there's no good way to store electric energy in the grid. So the generation pretty much instantaneously has to equal the load. Now, a nice thing about this is when you plug in your toaster, you're guaranteed you're getting fresh electricity. That electricity that you use was generated milliseconds before you use it. So it's always fresh. But we can't put you on hold. I mean, you can't get put in a holding pattern where, a lot of us flew here. If your plane the schedule's messed up, they just put you in a holding pattern. We can't give you a busy signal. So we've got to do this constant matching of generation with load. And another unique characteristic is, with few exceptions, there's no good way to control how power flows through the grid. So it's pretty much the electrons go where they want. We can predict where they're going. We can indirectly control them by where we make electricity, but we don't have big valves to open and close, for the most part, to change the flow on the grid. So some of the implications for renewable generation are that since a lot of these sources have almost free fuel costs, think wind and solar PV, these sources are operated at their maximum. So if a disturbance were to occur on the grid and you're running your wind at the maximum, you don't have any reserve there. So when we look for where do we get reserves, the only way we can get it from wind and solar PV is it would be to operate those resources so we're not taking advantage of all the energy in the wind. And you can just pitch the blade on a wind turbine to do this, but you're giving up free energy. I do want to say as we go forward with this talk, some renewable generation sources function pretty much like conventional sources like coal and natural gas. Examples are solar thermal, geothermal, and some of the biofuels like switchgrass. Take a biofuel and put it in a generator, it looks just like any other fuel from the controllability point of view. Okay, I'm going to give you a quick demo of how a disturbance will propagate through the power grid. The power grid has various time scales, of course. Lightning propagation is one of the fastest. Some of the slowers are boiler response and longer-term dynamics. What I want to show you here is how disturbance will go through the grid if, say, we were to lose a large generator. And the graph there on the left shows how the frequency will vary at different locations in the western interconnect for the loss of a large generator. And what I'm going to do is show you a visualization of this by playing a movie. And in this movie, it's going to start out, and you'll see the frequency at 60 hertz. Then you'll see colors propagate through the grid. That's how the frequency will decrease across the western interconnect as a result of a generation loss. And this is being played as it would really go. Okay, so this is a real-time playing, and let me reset that, hopefully. So that's 15 seconds of simulation. This is playing it again, then I'll play it a little bit slower. Yep. That's the black and white version for those of you in the 1950s. So this is playing in real time as it would really go. Alberta actually responds a little strangely because it's not that tightly interconnected. But actually, when you have a loss of generation in the southern U.S., the guys that feel it the worst are Alberta. Let me play that same one just a little bit slower. This is at 1/3 time. So that delay there is showing how fast that frequency disturbance propagates up from the south to the north, and then it's oscillating around. The point of this is when we're dealing with these issues, we have to respond quickly, because frequency disturbances propagate through the grid very quickly. Okay, so what happens during something like that? Well, initially when you lose generation, within the initial seconds, what you do is if you lose generation, you've lost sources of electric energy, you make up for that by stealing it from the rotating inertia of the large generators. They slow down, they're losing inertia, we're taking the energy and we're using it. The problem with trying to integrate in a lot of solar PV or wind is these sources do not let us see their inertia. PV has no inertia, and the newer wind systems actually hide the inertia from the grid. So we're losing inertia there. And then within seconds after the disturbance, there's devices called governors that respond by increasing the power output of the controllable generation. You've lost generation, there's devices called governors that sense the frequency's gone down, they open valves and they start to produce more electric power, and they cause the frequency to recover. Problem with solar PV and wind is if we're operating them at their maximum output, they've got nothing else to give. So it's okay if we just have a few, they're kind of riding on the existing generation, but if we want to integrate in 40, 50% renewables, we've got some issues to address. Well, how do we address it right now? Right now we use various units. They're either thermal units or hydro units. The thermal units, like natural gas and coal, can ramp very quickly. This graph shows, for that disturbance that I just visualized, how the output of a thermal plant would respond. Within a couple seconds, it's up about 7%, which is quite a bit. In contrast, a hydro plant is going to respond much slower, so that within 20 seconds after the disturbance, it's only gone up 2.5%. Wind and solar, on the other hand, aren't going to give anything. So if we want to integrate in a lot of renewables, we've got to address this issue. Well, minutes after the generation has been lost, then you try to make it up by changing your schedules. The graph on the bottom right shows the actual frequency for a disturbance in the eastern US, and the time scale on there is an hour. So about in the last 10 minutes, a generator is lost, the frequency goes down, and then it gradually recovers to 60 hertz. What's going on is that they're redispatching existing generation to make up for that. So if we can't use a lot of generation as we move towards a lot of renewable resources, we've got to replace that by something else, and that something else is load and storage. So one of the things we've been looking at is what are the ramifications on different generator design. And this graph here shows different designs on the generator, whether I've got a large amount of inertia or a small amount of inertia, whether I've got a fast governor, whether I've got a slow governor. The ones that respond the best, that is, they have the lowest frequency loss and the quickest recovery, is a high inertia with a fast responding governor. Okay, the ones that respond the slowest are when you've got low inertia and you've got slow governors or no governors. And that's what we would move towards if we want to integrate in a lot of wind. Okay, so what are the implications here? We need enhanced controls to deal with this, and that's what me and my colleagues at the other universities are working on. An advantage in going with more dispersed renewable resources is they're less likely to suddenly fail, but the problem is they can be subject to prolonged correlated changes. For example, there are places in the western system where there's a lot of wind being sited. I worked with Bonneville Power Administration in the Northwest, and there's a lot of wind going in the Columbia River Gorge. If you have a sudden drop in the wind in that area, you can lose a lot of generation, much more than I saw here. It won't go out all at once, but it'll go out in a prolonged sort of way over maybe minutes, tens of minutes, but we still have a net loss of a lot of generation, so we'd have to make up for that. Or you could say, what if we've got urban areas that have a lot of distributed PV on the rooftop, and suddenly cloud banks come in, and you lose across a large region a lot of distributed PV. So some of the possible control solutions are, one is you can take this renewable resources like wind and you can operate it at values below their maximum. And this is something that's done in Europe, where you might operate your wind at 95% of its maximum, so you've got some reserve. We can also go with more controllable load. That would be a good way if we can get the load to respond quickly, keeping in mind we need that fast response within seconds for it to help. Some people are looking at using wind controls to mimic the inertia. Certainly a wind turbine has inertia because you've got spinning blades there that you can pull inertia off of, so we can set up controls to do that. So we're looking on fast load controls to do that. One of the good signals that we can use is frequency. frequency actually provides a fast way of getting a signal out to the loads to do response. Another thing that we're looking at is the integration of pluggable hybrid electric vehicles. Pluggable hybrids, if they're charging and we can get a signal out to cause them to stop charging, that can be very useful. We need to have control to these PHEVs, because if everybody comes home at 5 p.m. and plugs them in, that's not a good thing to do. Storage is an issue. If we can get low-cost storage, and I know the next talk is on storage, that could be a game changer if we get low-cost storage in the power industry. We're also looking at wide area visualization, because getting the wide visualization of what's going on in the power grid, what I showed you on that graph is not available in utility control centers today. That's a picture of what the grid looked like on August 14, 2003, provides a nice view of how power is flowing in the system. The problem is it's not available, or it was not available in 2003. Your blackout in California in last month, the report's not out on it, so I'm not sure, but one of the newspapers mentioned that it was lack of coordination between different entities. Nobody saw the big picture. So that's it, and I'm open for questions.
Hi, Burton Richter. That was really fascinating. One of the things I didn't realize is the tightness of the frequency control. Now, I'm told that in the UK, they have much looser frequency tolerance, and therefore, their problems on integrating renewables are simpler. Can we loosen our frequency tolerance? What happens? My electric clock is perfectly happy as long as the integrated number of cycles in a day come out right.
Yeah, we're actually thinking about loosening the frequency, and the fact that we've had larger grids in North America has made it so that we have tighter tolerances. But yeah, that might be a solution, is to loosen the frequency tolerances. And electric clocks are no longer an issue, because you probably don't have any synchronous machines in your clocks anymore. Yeah, well. Okay. Yeah, go ahead.
Would more high voltage DC links stabilize the grid more by eliminating the requirement for tight frequency tolerance across the ends?
Well, high voltage DC provides a nice advantage in that we can control the amount of power going down the line. So it's a control that we can use. It does have a disadvantage that we lose some of the natural free-flowing ties that go between on the existing AC lines. So we might be able to build more DC, and you guys here in California have one of the largest DC lines, the Pacific Intertie, that brings power from northern Oregon down to southern California. So adding more DC is something that is being explored.
You could emulate the AC behavior.
Wait.
You can emulate. I'm a control theorist. I work.
Right. You can have on.
You can emulate anything on DC that you want on AC.
Right. You just need to get the right controls in to be able to emulate
yeah,
it.
we have computers and enough compute power to do that.
Yeah, I model this stuff, and I know there's issues.
I was curious, in the simulation that you had, the dynamics where the frequency control is sloshing back and forth from this transient. Are those resistive loads or constant power loads, or how much dynamics is there in the load that you're simulating?
Well, that model was using what WECC uses for their load, which includes a mixture of its constant current for P, but it also has induction motor model loads in it as well. So the induction motor model loads provide some of the dynamic response. But it's the standard model the utilities are using.
Thank you. Along the same lines of frequency control, I note that both photovoltaics and wind both have a frequency modulation in the way they're used. So is there a possibility that that could be used to actually be used as in a dynamic way to modulate the frequency in the event of an outage?
See, on a solar PV or a wind, the question is, are you running your control on the device to get maximum power out of it? And why wouldn't you? Okay, so if you're getting maximum power already, and I say give me more, you can't because you're at maximum. It's only by grabbing some of the inertia that you can do that. The solar PV has no inertia. A wind turbine does have inertia, but if you've got a more modern wind turbine design, you're not seeing that inertia from the electric grid side because it's going through an AC to DC to AC converter. So the option would be to say, I'm going to pitch my blades in normal operation so I'm not at maximum power output. So if I need extra power, I can put my blade so I capture that maximum power. The disadvantage in doing that is you're giving up free energy. And you know, the wind farms are going to be more reluctant to do that.
Yes, that's true. I didn't quite mean that. I meant more that not in terms of the power disparity, but more in terms of the frequency disparity, that with a large amount of renewables, there could be quite a big resource there to try and actually change the frequency of the grid. With PV, for instance, you can have whatever frequency you like, depending on the line commutation of the inverters. Is that a mechanism that could be used to actually feed in a different frequency to try and offset any fluctuation?
You know, I'm not sure about that. I'd have to think about that. But the problem you've got is if you need more power and your solar PV can't provide it, you can't provide it. All these devices, if you've got high frequency, they can respond to high frequency. And that's the standard control going into a wind turbine right now, is it'll pitch its blades to deal with high frequencies issues.
Okay, I think we need to move on. So let's thank our speaker one more time.
Thanks.
For more, please visit us at stanford.edu.